Good morning, all. Today I'm going to explain the basic concepts in optical communication system. So basically, in optical communication system, the signal which is used to transmit the information from the source to the receiver is nothing but a light signal. We are going to use light signal to transmit our information from the source to the destination. So here we need to study the properties of light signals in order to understand the transmission. So before getting into the detailed concept of optical communication systems, which deals with the different types of components involved in transmitting the information, we need to understand the basic concepts of light properties, light signal properties. Then only we can understand how the signal get propagated inside the optical devices and how it is going to be received in the receiver system. So coming to the ray theory transmission. So these are the basic concepts or basic terms which we need to understand before entering into the optical communication systems concepts. So what are these are the basic definitions involved in this ray theory transmissions are total internal reflection, acceptance angle, numerical aperture, critical angle. So these terms, we must be familiar with these terms in order to understand the light propagation, how the signal get propagated inside the optical fibers, and how in what way we can transmit the light signals in order to transmit the signal efficiently. So first we will deal with refractive index. This is one of the most important term in light signal, through which the propagation of light signal depends on the refractive index of the material, dielectric medium, what we are going to use. So to consider the propagation of light in an optical fiber utilizing ray theory model, it is necessary to consider the refractive index term. So what is the basic definition for refractive index? So the definition for refractive index is the refractive index of any medium, it can be any dielectric medium, is the ratio of velocity of light in the vacuum to the velocity of light in the medium. So the formula to calculate this refractive index is nothing but C by V, where C represents the speed of light in free space and V represents the speed of light in the given medium. So this term refractive index is very useful in understanding the propagation of light. So first we will deal with the term refraction. So what is refraction? So here consider in this diagram, we are going to consider the two medium. One is air medium and the other one is glass medium. So both are going to have different refractive indexes. Okay. So let us consider the refractive index of air may be N0 or N1, and or the refractive index of glass may be N2. So we can assume any one, N1, N2, that is our choice. And always refractive index is represented with the parameter N. So here in this diagram, here we are first we are going to pass the light signal. Okay, that is nothing but our incident ray. That is the original information in terms of light. Okay, we are going to transmit our information in terms of light. So that we will call it as the incident ray. Okay, so when the ray is incident on the dielectric, now we can see the horizontal line that shows the interface between the two medium, an air medium and glass medium. So this horizontal line represents the interface between air medium and glass medium, and at the origin, right at the origin, between these two interfaces, we are going our light signal is going to be incident. So we are going to pass the incident ray on the dielectric interface between two mediums. Okay, if light is if in the under this condition, if we are going to pass the light, okay, and this light will get refracted. Okay, this light will get refracted. Okay, in the diagram itself we can say that the light gets refracted with a particular angle. So the light get incident with a particular angle I, and the incident light, it is going to be refracted in the other medium, that is air medium, with an refractive index R. So when the ray is incident on the interface between two dielectrics of different refractive indexes, so for glass, the refractive index value is high compared with the air. So if we are going to transmit the light signal from the glass medium, okay, that is with the refractive index, high refractive index value, and it is going to be refracted if the signal get propagated in the low refractive index medium. So here air has lower refractive index value when compared with glass. So in such a condition, so we can consider if you are going to transmit the light signal with a the light signal incident, which is nothing but the incident ray with refractive index, higher refractive index value. Okay, the light signal will propagate from the medium of higher refractive index. Okay, and it get refracted if it travels in the medium of lower refractive indexes. That is the meaning for high to low. Okay, so this refractive index is briefly explained with the first diagram. So here in the first diagram considered, here we are going to take two refractive index, two dielectric medium. One is glass and other one is air. And the refractive index of glass is, as I already said, the refractive index of glass is high. Let's take that as N1, and the refractive index of air is always low when compared with glass, and take that as N2. Okay, now this is the horizontal line that is going to act as a interface between these two dielectrics. Okay, so under this condition, if you are going to pass the light signal, that ray is called as incident ray with an angle pi 1. Okay, here we must be thorough with the term, that is pi 1, pi 2, and those terms are very important in describe the properties of light signal. Okay, so the incident ray, the incident ray, which is nothing but the ray which is incident on the dielectric interface between two dielectric with an angle pi 1. Okay, and this light signal will get it may be refracted or it may be reflected. That depends upon the condition, okay, of these incident as well as refractive incident angle as well as the refractive angle. Okay, now consider the case 1. Case 1 is the incident ray will get completely refracted. Okay, completely refracted if the condition, these two conditions are satisfied. The condition 1 is N2 is less than N1. Here N2 is nothing but refractive index of um, air, and N1 is nothing but refractive index of glass. Okay, so if the refractive index of air, that is the second medium, is less when compared with N1, and at the same time, if the angle created by the light signal, that is pi 2 at the medium 2, okay, it is greater than pi 1. If these two conditions are satisfied, automatically the signal will get refracted as shown in the first diagram, that is A. Okay, that represents the refraction. So when N2 is less than, okay, when N2 is, correct, when N2 is less than N1 and pi 2 is greater than pi 1. So can you check this condition with this diagram? See the diagram, in the diagram, N2 is less than N1 and pi 2, this pi 2 is greater than pi 1. Okay, if these two conditions are satisfied, automatically the ray which is incident on the interface between two dielectric will get completely refracted. Okay, that is represented as an exit ray in the diagram A. And come to the so these two conditions are very much important for refraction. Okay, so this is the first case. And coming to the case 2, okay, we need to go for deals with the here pi 1, pi 2, N1, N2. As I already said, the term pi 1, N1 represents the high refractive index value of glass, and N2 represents the lower refractive index of air. Okay, and here pi 1 and pi 2, which is nothing but the incident angle, and pi 2 represents the angle of refraction. Okay, so you must be with the you must be thorough with the parameters N1, N2, pi 1, pi 2. N1 is refractive index of glass, N2 is refractive index of air, and similarly pi 1 is the incident angle of incident or incident angle, and this pi 2 represents the angle of refraction. Okay, so these terms we must be familiar with these terms, and this is the first basic definition which we must be thorough in in studying the optical signal. So the very first definition what we have learned is refraction. So the most important condition for refraction is N2 must be less than N1 and pi 2 must be greater than pi 1. So if these conditions are satisfied, automatically the signal will get refracted. Okay, and coming to the next concept in the optical communication system. Okay, the basic concepts of optical communication system, which is nothing but Snell's law. So this Snell's law is very, very important in exam point of view, and it is also very important law which is in the optical communication system. Okay, so the angle of incident and the refractions are related to each other. Okay, The definition for the Snell's law is I'm giving. So the angle of incident, okay, that is nothing but pi 1, and the refraction pi 2 are related, they are related to each other, and the refractive indexes values are also related to each other. So we need to take consider this diagram. Okay, this pi 1 and pi 2 are related, and this n1 and n2 are related to each other with some formula. That is nothing but n1 sine pi 1 is equal to n2 sine pi 2. This equation represents the Snell's law of refraction, or simply we can rearrange this equation as sine pi 1 by sine pi 2 is equal to n2 by n1. So this final equation represents this Snell's law of refraction. Okay, always the refraction phenomenon should satisfy this Snell's law. Okay, so this is the very important thing. And next, coming to the a critical angle. Okay, so the second definition is Snell's law, and the third term is critical angle. So this critical angle is represented with the angle pi suffix c. C represents the critical angle. Okay, so what is critical angle? When the angle of refraction is 90 degree and the refractor ray emerges parallel to the interface between the dielectric, then that angle is nothing but the critical angle. Okay, so we can say that we can justify this definition with this particular diagram. See, come to the second diagram B. This angle represents the critical angle. So critical angle is nothing but the angle at which the incident ray, the light is incident on the dielectric. Okay, it get exited, okay, get exited, or it is going to be refracted in the axis parallel to the um, axis or original axis. Okay, so we can say we can justify with the definition. It is 90 degree when the angle of refraction is 90 degree and refracted ray emerges parallel to the interface. See, angle of refraction is 90 degree. Now we can say that the angle, this is the refracted ray. Okay, this is the incident ray. In the take this diagram being this line represents the incident ray, and this dark line represents the refracted ray. Okay, here which under which condition this incident ray will make an angle pi c. It means the ray which is get refracted must be parallel to the, that is very important, parallel to the interface. Okay, this is the interface line, and this refracted ray and the interface line they are going to resemble parallel to each other. Okay, so this will form only with the angle 90 degree. Okay, if the refracted ray forms 90 degree with the axis and it is going to be parallel to the interface between two dielectric, then at this angle, okay, at this time, okay, this is the angle at which it is going to emerge as parallel. So this angle is nothing but critical angle. So if the angle okay, if you are going to pass the light ray on the interface with some particular angle, and that angle in which the emerges, this angle makes the light ray to be refracted parallel to the dielectric, okay, interface between two dielectric, then this angle is called critical angle. Okay, so that is very, very important term which we must be we must know that, okay, in the optical communication system. Okay, so this is the limiting case of refraction, and because after that, okay, this is one of the limiting case of refraction phenomenon, and the angle of incident is called critical angle. Always the critical angle is nothing but the incident angle, but this incident angle we will call this incident angle as a critical angle only if it makes a refractor ray which is in the that is refractor ray to parallel in the axis, parallel to travel in the axis parallel to the dielectric between two interfaces. Okay, so simply we can replace this critical angle with the help of this Snell's law. Now we can say that here pi 2 is going to be 90 degree. Take this Snell's law equation. We need to justify this critical angle in this equation, and we need to find the equation for critical angle. So now according to critical angle, the angle of refraction, that is pi 2 is 90 degree. Yes, when we are going to substitute this 90 degree here, okay, sine 90 value, then we can rearrange this equation as sine pi c. So this because I have said to you, the pi 2, when pi 2 is equal to 90 degree, then the angle of incident is nothing but critical angle. Yeah, we can call this as pi 1 as, we can replace this pi 1 with the term pi c. So sine pi is equal to sine, so substitute the value. Sine pi 2, no, no, pi 2 is equal to 90 degree. So sine 90 is nothing but 1. So we can rearrange this equation as n1 sine pi c. Here the incident ray should be replaced with pi 1 is replaced with pi c. Since for pi 2 equal to 90 degree, the incident ray is called critical angle. So we can replace pi 1 by pi c. So n1 sine pi c is equal to n2. Okay, n1 sine pi c is equal to n2. From that, sine pi c is equal to n2 by n1. So this is the equation for critical angle. Okay, so this is the next important term which we need to be studied in the optical communication system. And the most third important term is total internal reflection. So all the transmission, okay, of light signal inside the optical fiber is done only with this phenomenon, total internal reflection. Shortly, it is represented as TIR. So we need to thorough with the basic definition for this total internal reflection. When the angle of incident is always greater than the critical angle, the light is reflected back into the original dielectric medium with a higher efficiency, around 99.99%. This is the definition. When the angle of incident is greater. So what is the angle of incident? Which is nothing but the pi 1. S or I. In this diagram, we can say that I. When the angle of incidence is greater than the critical angle. Okay. So when I is okay greater than critical angle, when we are going to increase, okay, when we are going to increase the incident angle greater than the critical angle pi c, then the signal will get reflected, okay, reflected back into the same medium. Okay, this can be say justified with the third diagram. See, now we can say that this pi is nothing but what, our critical angle, our the incident ray. So we compare this pi c with this incident ray. See here, this pi, okay, the incident ray pi is greater than pi c. That is the definition I have read previously. So when the angle of incident is greater than critical angle, then the light get completely reflected. Instead of refraction, it gets reflected in the same medium itself. Here, the medium what we have considered is glass medium. So the incident ray travels in the glass medium, and the same reflected ray also travels in the same medium, making some angle pi. Okay. So this is the condition for total internal reflection. So total internal reflection happens only when the incident ray is greater than the critical angle. I think you might got a clear idea regarding the basic terms involved in optical communication system. So the thing what I have explained is is given in this diagram. So first one is refracted ray, second condition is critical angle condition, and the third condition is total internal reflection condition. Okay, so these are the basic terms. You must be thorough with the optical communication system. Next, coming into the fiber. Okay, this is the structure. This diagram represents the basic structure of optical fiber. Here in optical fiber, basically we had a two thing. One is the center part. Okay, the core that is called as core, and the other outermost covering is nothing but cladding. Okay, the light signal, it is going to be transmit, okay, completely inside the core only. Okay, with the help of the phenomenon called total internal reflection. So the total internal reflection occurs only inside the core, and this cladding, okay, is going to act as a outermost cover of this core, which is going to protect the core, okay, from some losses, okay, and dispersion phenomenon. So the total internal reflection phenomenon plays a very important role in transmitting the information from the source end to the destination end. Okay. And the next important term which we need to know is acceptance angle. Okay, this angle is represented with the term theta A. The suffix in the suffix we need to represent the term A. This A represents the maximum angle to the axis. Okay, acceptance angle theta A represents the acceptance angle, which is nothing but the definition is the maximum angle to the axis at which light may enter the fiber in order to be propagated, or it is often referred to as acceptance angle for the fiber, which means that take this diagram. Okay, we are going to pass the light, okay, light rays inside this core, and the most important thing is take this diagram. This is the center part is core part, and the outermost part is cladding part. The core is completely surrounded by the cladding, and we are going to pass some light signal inside this core at the interface. So this medium is we need to consider two medium. One is glass medium and the one is air medium. So you are going to pass the light signal from one medium, and it is being transmitted inside the optical fiber. Okay, so this angle, acceptance angle, is represented in this diagram as theta A, which means that this is the reference axis which travels along the center of the core, and the theta A, okay, the cone in the diagram, a conical area is represented, is shown in the diagram, which means that you can transmit the light signal within this cone area only. Okay, if you're going to transmit the light signal outer of this cone area, then we can't transmit our information efficiently. The signal may get reflected, or it may be lost. Okay, loss may occur. So the basic condition for transmitting the light signal inside the optical fiber is we should transmit the light signal, that is our incident angle, okay, incident ray should be within this cone area. Okay, that angle. So it makes some particular angle with the reference axis. That angle is nothing but the acceptance angle. So these cone is called as acceptance cone. Okay, where that means that we can transmit our information light signal within this area. Okay, at any angle you can transmit the incident ray inside the optical core, optical fiber core, and outside of this, if you are going to pass the outside of this acceptance cone or cone area, if you're going to transmit the right signal, it may get lost, and we can't receive the information efficiently. So acceptance angle plays a very important role. It is a maximum angle to the axis at which the light may enter into the fiber. So beyond that, we should not transmit our light signal, okay, in order to be propagated. And this theta A is sometimes referred to as maximum or total acceptance angle. Total acceptance angle. Okay, so this is the most important definition, acceptance angle. And the next definition is numerical aperture. Okay, so this, what is numerical aperture? It is used to describe the light gathering or light collecting ability of optical fiber. So light gathering or light collecting ability, how far the optical fiber it is going to collect the information. Okay, that is nothing but the numerical aperture, and always it is used to measure the magnitude of acceptance angle. Okay, mathematically. Okay, so we can say, we can justify, okay, this numerical aperture, how far the signal is going to be collected inside the core. Okay, that is nothing but the numerical aperture. Okay, it's some type of measurements only. Okay. So a light ray here in this diagram, you are going to pass the light ray incident on the fiber core at an angle theta 1 to the fiber axis, which is less than the acceptance angle theta A. So theta A is going to be here, and I'm going to pass the light signal which is less than theta A. Okay, the ray enters into the fiber from the medium. So the from the medium of air to the medium of glass. Okay, so medium of air has refractive index N0, and fiber core has refractive index N1. Then by Snell's law, we can write N0 sine theta 1 is equal to N1 sine theta 2. Okay, now using this equation, we can go for determining the equation for numerical aperture. Okay, so in the numerical, while we need to, before getting finding the equation for numerical aperture, consider this light ray, okay, falls on see the light signal travels from the air medium to the glass medium. So air medium has a refractive index N0 and glass medium has a refractive index N1, and that is nothing but the core, and the cladding has a refractive index N2. Now we are going to transmit the incident ray at an angle theta 1 with respect to the fiber axis. This dotted line represents the fiber axis, and it is always, this theta 1 is always less than theta A. So it is going to satisfy for maximum efficient transmission. Okay, so theta 1, and this light signal, it gets reflected inside the optical core with making some angle pi, okay, with respect to the fiber axis. So now let us go for the mathematical derivation of this numerical aperture. Let plot this term as A, B, and C, which forms a right angle triangle. And uh, So for the right angle triangle, okay, for the right angle triangle ABC, we can write a 90 plus theta 2 plus pi. See, 90. This the angle, here the angle is 90 plus theta 2 plus pi. This the total angle of this right angle triangle is 180 degree. So we can write 90 plus theta 2 plus pi is equal to 180 degree. Okay, from that pi is equal to 180 minus 90 minus theta 2. The equation becomes 180 minus 90 is 90. 90 minus theta 2. So, or we can write theta 2 is equal to 90 minus pi. Okay, when we are going to substitute this equation in this equation, theta 2 equal to 90 minus pi, sine 90 minus pi becomes cos pi. So, n naught sine theta 1 becomes n naught sine theta 1 is equal to n1 pi 2, right? Am I right? n1 cos pi, n1 cos pi. So, using the trigonometric relation sine square pi plus cos square pi is equal to 1, we can write cos pi can be written as 1 minus sine square pi root of or whole power 1 by 2. Yes, cos pi is equal to root of 1 minus sine square pi. Or we can write 1 minus sine square pi whole power 1 by 2. Okay, that is written here. So n naught sine theta 1 is equal to n1. In the place of cos pi, we can write 1 minus sine square pi whole power 1 by 2. Okay, and again, by applying the Snell's law equation, okay, we can write acceptance angle in terms of, we have already wrote the equation for acceptance angle. So replacing that with theta 1 with the acceptance angle, because our theta 1 is going to satisfy the acceptance angle. So we can write n naught sine theta a is equal to n1 into, in the place of sine square pi, we can write what we can write n2 by n1 according to Snell's law. So n1, so take simply, I'll take LCM and simplify that. So we'll get the term n1 square minus n2 square whole power 1 by 2. So with this, the numerical aperture can be concluded with the equation n naught sine theta a is equal to n1 square minus n2 square whole power 1 by 2. Okay, this is the basic mathematical equation for finding numerical aperture. And this is very important term in optical communication system. Then only we can determine how far the signal has, the optical fiber has collected the signal efficiently inside the core and transmitted at the destination end. Okay, thank you all.